In this video, I would like to present our recent paper, Explainable Deep Learning to Classify Royal Navy Ships. It was co-authored by myself. I'm connected to the Faculty of Economics and Business at KU Leuven and to Southampton Business School, which is part of the University of Southampton. Amy Adams and Rodrigo Pacheco Ruiz, both is affiliated with the National Museum of the Royal Navy. My daughter, Anne-Sophie Basens, who is a student at KU Leuven and helped with some of the data pre-processing and labeling, as I will discuss later. And my ex-PhD student and colleague Professor Seppe van der Broeke, who is a professor at Ghent University and also a guest professor here at our Faculty of Economics and Business at KU Leuven. Here's the overview of the video. So we're going to start with a brief introduction by situating the need for the research. Then we're going to highlight the key research contributions. We will briefly summarize the literature, then get into the data collection and labeling, then extensively discuss the data pre-processing and the various tweaks and procedures that we adopted there to boost the performance of the deep learning models. Then we're going to get into the convolutional neural networks, which are the type of deep learning models that we have adopted in this research. We're going to extensively discuss how we configure those CNNs, those convolutional neural networks, how we trained them, how we made sure there was no overfitting, etc., how we measured the performance. And then we're going to also obviously discuss the results. We're going to showcase what performance was obtained on our data set. We're going to look at performance from various perspectives, present various types of plots, tables, etc. And then we're going to conclude by adding an explanatory facility to the deep learning models. More specifically, we're going to discuss how we can interpret the deep learning models using very nice visualization facilities. First, if you look at many digital archives and museums across the world, many of them gather all kinds of data, typically in enormous volumes. In other words, what they store is essentially big data. Big data in the sense of its volumes, but also in the sense of the variety thereof. You're going to see massive amounts of textual data, but also massive amount of images, massive amounts of videos, etc. All of these are essentially highly unstructured data, which are stored into digital archives, ready to be analyzed using state-of-the-art analytical techniques. Analytical techniques such as artificial intelligence, more specifically deep learning. The emergence of artificial intelligence and deep learning, together with hardware accelerators such as graphical processing units or GPUs, has created new opportunities for digital documentation, management, and archiving. In this paper, we're going to use convolutional neural networks as one type of AI, as one type of deep learning technique for ship classification, to classify ships as destroyers, cruisers, frigates, etc. We will focus on military ships. More specifically, we will use a unique dataset that has been provided to us by the National Museum of the Royal Navy, the Wright and Logan collection, to be more precise. So what are our research contributions? Our research contributions are that we present a very robust and reproducible deep learning methodology for ship classification. The deep learning methodology will make use of state-of-the-art convolutional neural networks to make sure that we have deep learning models that are highly performing at classifying ships as destroyers, cruisers, frigates, corvettes, etc. We will also make sure that we make use of state-of-the-art visualization methods such as Grad-CAM to make sure that we also add interpretability to the deep learning models we have estimated. We will extensively study the importance of data pre-processing. Data pre-processing is vital in any type of analytical exercise, also in our particular setting. But in our particular setting, since we're dealing with images, we have to adopt very specific types of data pre-processing, such as image segmentation and image augmentation. We will discuss both extensively and also the interplay between them. We will also, one of our final research contributions is that we make our Python Tensor Keras code available as open source so that it can be easily reused by other researchers or practitioners in the field of digital archiving. First, let's have a look at literature review, and we will focus on ship image classification. And to do image analysis, convolutional neural networks are the state-of-the-art technique. They're a type of deep learning method that act or operate as a feed-forward neural network designed to extract image features by applying filters, also called kernels or feature detectors, to images. More specifically, each filter kind of represents a particular image pattern, which is systematically traversed over the image's pixels, while convolutional operations amalgate the input filter, the image input and the filter to generate a set of acquired features. As the network progresses through its feed-forward layers, the features evolve. They become progressively more meaningful and more intricate. Essentially, what a CNN does is it performs a hierarchical decomposition of an image, commencing with very fundamental features such as lines, edges, contours, corners, and colors, before progressing to more complex features like shapes, like rectangles, like circles, like ellipses, and ultimately then recognizing high-level, very meaningful concepts such as, in our case, a submarine's fin, a destroyer's gun turret, or a carrier's flight deck in the deepest layers of the CNN. Popular examples of CNN architectures are ConvNeXt, which have been very recently developed by Liu et al. In 2022, EfficientNet, developed by Tan and Lee in 2019, and ResNet, which has been quite popular for image classification and has shown very good performance in various benchmarking studies and was developed by He et al. In 2016. Now, since these deep learning architectures are really huge architectures in terms of the layers or parameters or weights that need to be estimated, many of these techniques have been pre-trained using a publicly available database, more specifically the ImageNet database. And the ImageNet database is an image repository of about 15 million annotated images spanning 1,000 distinct classes, each aligned with the well-known WordNet hierarchy, so including classes such as goldfish, cowboy boot, broom, container ship, and so on. So what we will do is we will use pre-trained CNNs and then fine-tune them, tweak them to the ship images that we have been provided with from the National Museum of the Royal Navy. Ships can be classified according to various sources. They can be one example of a source is acoustic signals captured typically through hydrophones, which record the radiated noise emitted by ships. This noise or these signals or audio streams can then be readily transformed into spectrogram images, which are visual representations presenting a time-varying visual depiction of the frequency spectrum, as such leaning itself for analysis using CNNs or convolutional neural networks. Other input sources that can be used to classify ships are, for example, synthetic aperture, radar, or SAR data emitted from radio waves or satellite imagery data. Or we can make use of, as I already mentioned, of a repository of ship images. And one very popular example of a public repository of ship images is the MARVEL, which stands for Maritime Vessel dataset, which comprises about 140,000 distinctly labeled maritime vessel images spanning 26 diverse types of vessels or ships, covering both military and civilian ships. In our study, however, we will make use of the Wright and Logan collection, as I already mentioned. The Wright and Logan collection, well, actually, Wright and Logan was a Portsmouth-based photographer who specialized in portraits of British Royal Navy ships entering and leaving the key naval base in Portsmouth Harbor during the period 1924 and 1998. So our data set spans the period between 1924 and 1998, and we have about 3,533 black and white images from that period of warships. We added external data to our data set so as to make sure that our convolutional neural networks would be able to perform really well, so as to give them more facilities as to learn meaningful patterns from data. So we scraped about 786 images from navalhistory.net and also 1,324 images from uboat.net. The way we labeled each of the ships was by making use of all kinds of reference works, like Conway's All the World's Fighting Ships. That was a very useful book, and Jane's Fighting Ships. So you see that you have several editions of each of those reference works spanning different periods in time, and then discussing all the ships that were available during that period as part of the Royal Navy. We obviously also made use of Google and Wikipedia to help us with the labeling, and we spent about 1 man-month of manual labeling. Here you can see some examples of ships that are part of our Wright and Logan collection. Because I'm a history geek, I would like to give some further information. At the top left corner, we have HMS Daring, pictured in 1932. HMS Daring was actually torpedoed and sunk by a U-boat close to Scapa Flow in 1940. The top right, we have HMS Perseus, which is a submarine, and pictured in 1932. HMS Perseus was sunk by an Italian mine close to the Greek island of Zakynthos in 1941. Bottom left, we have the well-known dreadnought battle cruiser HMS Hood, pictured in 1918, and she was sunk during the Battle of the Denmark Strait by the German battleship the Bismarck in 1941. And at the bottom right, we have HMS Hermes, which is a carrier. As you can see, she's pictured there in 1953, and she actually actively participated in the Falkland War. We developed, to facilitate the labeling, we developed a web-based Python app. Here you can see where we loaded all the pictures and where we could label them. And as you will see that you can see that there's lots of categories that we can assign the images to, like aircraft, transport ship, amphibious assault ship, battle cruiser, battleship, carrier. You can see that this is Ark Royal, which is obviously a carrier, corvette, cruiser, depot ship, destroyer, and so on. So during the analysis, we will not consider all these types of classes. We will only pick a few of them to make sure that we have enough observations in each of the classes to make sure that we can estimate a meaningful convolutional neural network. So we'll have to group some of these classes in a particular way in order to do a good analysis. During the data pre-processing and during the data collection and labeling, some images were removed. There were various challenges that we actually faced. First of all, we removed unclear images, those, for example, featuring multiple ships, images with very intricate backgrounds, such as depictions of harbors, zeppelins, or flying helicopters or jets, ship images with dense smoke clouds emanating from the ship's funnels, or images with very extensive textual elements, like, for example, postcards, etc. Or also images with heavily damaged ships. So I remember that we removed HMS Victive because we had an image of it, but it was heavily damaged after the Zeebrugge raid. Also, images offering us glimpses of the ship's interiors were removed during the data pre-processing. A couple of caveats we had to deal with. First of all, there was reuse of ship names. For example, HMS Churchill, that you see depicted right here at the bottom, was a destroyer in World War II. So this is the picture we have right here to the bottom left, whereas it was a submarine in 1970, as you can see in the middle picture right here. We also have varying ship architecture. So the first types of carriers, actually, like the first types of carriers, here you can see an example of a carrier, which is HMS Barham. They were typically just battleships with very small runways constructed above the ship's forecastle, as you can see right here, the very small runway to make sure that the plane can successfully take off. So you can see that the architecture of those first types of carriers is very different than architectures that we will see later in time during the Second World War and after that, which is going to make it a lot more complicated for the convolutional neural network in order to successfully label these images. Furthermore, what we also had is that some of the ships had been refitted. There were about 23 destroyers that had been refitted to frigates between 1949 and 1957, but we had images before and after the refitting, which obviously also complicates the deep learning exercise. Pennant numbers, some images had very clearly visible pennant numbers, which made it very easy for us to label the images. But though the pennant numbers are reliable, they're very reliable, they are not perfect. Usually F stands for frigate, and it will be correct in about 99% of the cases. MNJ for minesweeper, C for cruiser, but L could denote a landing ship or a destroyer. We gave some examples of that in the paper in case you're interested. Here you can see the distribution in our data set. So you can see that you can see the distribution in the internal data, so the data from the Wright and Logan collection, and the external data, the data that we scraped from uboats.net and naval history, which is denoted in red. So you can see that the most prevalent class is the destroyer. Most of our images relate to destroyers, whereas the least prevalent and hence the most difficult to classify class is the corvette class, as you can see right there. It is important in any type of analytical exercise to do good data preprocessing. The first thing that we did to facilitate the training of the deep learning models, we uniformly resized all images to a maximum width and height of 720 pixels, which was quite a resource-intensive task since we had some very high-resolution images. And to do that, we used Python's Pill imaging library. And then we looked at image segmentation. And the idea of image segmentation is to remove irrelevant objects like skyline, water, harbor objects from the picture, such that the deep learning technique, in our case the convolutional neural network, can fully focus on the ship's essential architectural elements. To do this, we used a package that was provided by Meta AI, which is called the segment anything model package. And the segment anything model package allowed us to actually automatically remove some of these objects. So you can see that although the SAM filtering is definitely beneficial, it's not perfect. It will not always deliver perfect results, and traces of the background could still persist in some of the processed images, as can be seen for HMS Agincourt right here. You can see that there's still some smoke here, which in the ideal world would have been removed during image segmentation. Note that HMS Agincourt was a battleship that was later on sold to the Ottoman Empire. Here also for HMS Acasta, which was a destroyer sunk by two German battleships in 1940, you can see some of the harbor persisting right here. And here for HMS Repulse, which was successfully decommissioned, and here you can see it pictured in 1968, you can still see that after the image segmentation, part of the harbor actually still persists in the image. So the image segmentation works nice. It will definitely contribute to the performance, but it will not be perfect. What we then also did was image augmentation. And the idea of image augmentation is to start from one image and generate various variants thereof. You generate various variants thereof because that way you increase the data set size. You give more images to your convolutional neural network such that it will have more opportunities to learn meaningful discriminating patterns between different types of ships, such as cruisers, destroyers, frigates, and so on. So the idea is to generate synthetic images, add them to the training data, you get a bigger training data so that the deep learning model will perform better. We do that by horizontal flipping, by cropping, by blurring, by sharpening, by resizing, by adding spatter, by adding Gaussian noise, blur, or simulating fog. And usually you do all these different types of operations simultaneously. So here you can see one source image to the left of HMS Capel. She was actually a frigate that was torpedoed and sunk by a U-boat close to Cherbourg in 1944. And here you can see 4 augmented images by actually applying the operations we mentioned right here. However, now we have discussed image segmentation and image augmentation, and the initial experiments showed us actually that the performance declined after augmentation. So if we did segmentation first and then augmentation, the performance of the CNN models that we are about to estimate later on significantly decreased. And this is quite obviously due to the spatter, fog, blur, or noise that we added to the already segmented or cleared up images. So if you start adding spatter, fog, blur, or noise to images that have been properly segmented, that will not be to the benefit of the deep learning CNN model at all. So it's better, so that we can actually, to deal with this, we can pursue two options. We can do the augmentation before the segmentation, but this is really resource intensive and not scalable. Or we can opt to only do safe augmentation methods. Here you can see safe augmentation methods being applied to the battleship HMS Agamemnon. Safe augmentation methods include horizontal flipping, sharpening, rotation, image resizing. So we're not adding any noise, we're not adding Gaussian blur, we're not adding spatter. We just do very safe augmentation to make sure that we do not undo some of the effects of the segmentation. Okay. Now we're ready to start our deep learning model. So here you can see an image, for example, HMS Vanguard. She was a battleship that was sunk by an internal explosion at Scapa Flow in 1917. And here you can see how a CNN model architecture typically looks like. So we have different types of layers. As I told you earlier, it's a feed-forward neural network. And those layers have weights that represent filters, as I already discussed, feature detectors, kernels, etc., that can be pre-trained. And the way they can be pre-trained is by making use of the ImageNet database that we referred to earlier on. Remember? So many of these weights can be pre-trained on the ImageNet database, and then we add a global average pooling layer. The global average pooling layer, what this is actually doing, is actually pooling the feature maps into one overall value, which is then fed to a dense head. So in other words, the two-dimensional global average pooling layer calculates the average values of each feature map and then feeds that to a dense head in order to see whether we're looking at a battleship, a cruiser, a carrier, or a corvette. These CNN networks were then trained, and we had various variants thereof, which have been discussed in the literature. We looked at plain vanilla CNNs, ConvNeXt, which are the most recent type of CNNs, ResNet, which has proven to be very performing in earlier benchmarking studies, and EfficientNet. To make sure that there's no overfitting, we applied dropout, and the idea of dropout is to randomly deactivate specific network nodes or weights during training, determined by a predefined dropout probability. You can see that the dropout probability in OR methods was always 40%. We used two types, or we experimented with two types of loss functions: cross entropy error, which is the type of loss function that comes with a softmax activation function in the output layer. So that's the standard loss function. Or focal loss. Focal loss is a kind of more advanced variant of cross entropy loss that is very suitable to deal with data in which we have an imbalanced class distribution, in which one class is more prevalent than another class, as is the case in OR datasets. Like in OR dataset, we have a lot of destroyers and we don't have a lot of corvettes, remember? We optimized them with the ADAM optimizer. ADAM stands for Adaptive Momentum Optimization, which is the standard optimizer in deep learning models. And we also contrasted it with a transformer method, ConvMixer, that was also recently suggested. Here you can see what the basic model configurations told us. So the basic model configurations for each of those architectures, so a basic CNN, ConvNeXt, EfficientNet, ResNet, and ConvMixer, are shown here. Transfer learning indicates whether we make use of features that have been previously learned on the ImageNet database. So remember, the ImageNet database, that was a repository of 15 million images that we could use to pre-train. So you can see that in most of the cases, transfer learning was useful. Then we also looked at whether the external data was useful, yes or no. So the data obtained from naval history or uboats.net. You can see that rather surprisingly, the external data most of the times, well, actually in 3 of the cases, did not add anything to the performance at all. And then we also looked at focal loss, yes or no, and you can see that in 3 out of the 5 cases, focal loss, so the special type of objective function or loss function that is particularly focused on imbalanced classes, adds value to the basic CNN architecture, to the EfficientNet, and to the ConvMixer. So here you can see our optimal model configurations. Let's now have a closer look at the results, because here you can see various types of models that we have covered. So a basic convolutional neural network, a ConvMixer, a ResNet with 50 layers, an EfficientNet, and a ConvNeXt. And the graph depicts the zero-notch performance accuracy, which represents the model's accuracy when its prediction corresponds to the class with the highest output probability, a principle that we commonly refer to in machine learning as the winner-take-all principle. We also depict the one-notch and two-notch accuracies, on the other hand, which measure whether the true target, destroyer, cruiser, frigate, etc., lies within the top 2 or 3 most likely predictions generated by the convolutional neural network. From this picture, we can clearly see that the ConvNeXt is the best performing. Its zero-notch performance accuracy reaches almost 80, and its one-notch performance accuracy reaches almost 95, which is quite spectacular if you ask me. Here you can see the confusion matrix. The confusion matrix contrasts the actual versus the predicted classification. So here we have battleship, carrier, corvette, cruiser, destroyer, frigate, mine, sweeper, and submarine. And you can see that obviously the ones that are most easy to recognize are the submarines and the carriers because of their particular architecture. Note that correct classifications are on the diagonal and denoted in boldface. Erroneous classifications or wrong classifications are off diagonal. So here we can see one submarine, right here, one submarine which is classified as a carrier, right? I'm going to come back to that later on. We can now summarize this confusion matrix in terms of precision and recall. Precision assesses the accuracy of a prediction, so how confident can we be in the prediction, while recall gauges its completeness. Here you can see that for submarine, if we classify a boat as a submarine, we can be 100% sure that it is indeed a submarine, right? You can see that in this column here. If we predict something as a submarine, turns out that in our test set, which is 20% of the observations, that we had 32 submarines. All of them had been correctly classified as a submarine, right? So that gives us a precision of 100%. If we classify something as a submarine, then we can be sure that it is a submarine. That does not mean that we classify all submarines correctly, because there's actually one submarine that is classified as a carrier. And that is reflected in a lower recall, because we don't recall all the submarines, right? So precision tells us how confident are we in our prediction. So when we classify an image as a submarine, we can be very confident. Recall tells us how many of the actual submarines do we recall. The recall is not 100% because there's one submarine right here that we don't recall, right? And you can see that for submarine and carrier, you can see also for carrier, the precision is very high. The recall is also very high for carrier. But for corvette, for example, is a lot more lower. Also for frigates is a lot more lower. So it's a lot more difficult to differentiate those from the others. Let's have a look, just out of mere curiosity, to this one particular submarine that is classified as a carrier. This is what you can see here. This is HMS Truculent, which is classified as a carrier. It's a submarine. The reason it is probably classified as a carrier is because of its somewhat unconventional design, characterized by its unusual fin, as you can see right here, an armament, which likely led the ConvNeXt model to misclassify it as a carrier. Note as an anecdote that this submarine, Truculent, she actually sank in 1950, after the Second World War, by accidentally hitting a Swedish tanker. Okay, so now we want to look at how we can interpret deep learning models, because now we have built those models and we see that they're quite well performing. So it would be nice if we can also shed some light on their internal functioning and see how we can interpret them. This falls within the realm or research area, which is also called XAI, explainable AI, and there have been various methods that have been suggested to make black box models like convolutional neural networks more explainable, such as Shapley values. Lundberg and Lee were amongst the first to use Shapley values in a machine learning context. Counterfactuals for CNNs, like my ex-PhD student together with one of his colleagues, my ex-PhD student David Martins together with one of his colleagues did some very nice work on that. In this paper, we used gradient weighted class activation mapping, also called Grad-CAM, suggested in 2017, which is a very nice visualization of what elements of the image contribute most to its classification by looking at gradients. In other words, it uses the gradients of any target, cruiser, frigate, carrier, submarine, flowing into the final convolutional feature map to produce a coarse localization map highlighting the important image regions. The image regions that really contribute a lot to the final classification. In other words, what we're doing is we're looking at large gradients in order to see what parts of the image contribute most to the classification. And here you can see that visualized for four boats, four ships. Upper left, we have HMS E11, which is a submarine which played a pivotal role in the Dardanelles battle, which took place between 1915 and 1916. And we can see that the Grad-CAM visualization clearly highlights the essential parts of the sub, which are its fin, right? So we have the submarine's fin, which is highlighted here, and sections of its casing, as you can see right there. Adjacent to this image, we have HMS Ark Royal, right, where you can also see that the Grad-CAM image clearly highlights its distinctive ski jump ramp, which we have right here, which is used for takeoff and landing of the planes. Here we have the Grad-CAM image of HMS Gavington, which is a minesweeper, where the conspicuous highlights clearly demarcate the ship's minesweeping equipment, as you can see here positioned at the stern. Here we can see the Grad-CAM image for HMS Dreadnought, which is a battleship, where we have a very nice discernible edge detection feature extending up to the ship's top antennas. So you can really see, using these Grad-CAM visualizations, what the deep learning model focuses on in order to make its classification. So it's a very handy feature in order to shed some light on the internal functioning of the convolutional neural network, and as such add explainability, interpretability to the deep learning model. So to conclude, we used a very unique data set that was obtained from the National Museum of the Royal Navy. We used the Wright and Logan data set, and we analyzed it using state-of-the-art convolutional neural networks such as ConvNeXt, ResNet, EfficientNet, and ConvMixer as a transformer for ship classification. We found that ConvNeXt is the best CNN with an impressive zero-notch accuracy of about 80% and a one-notch accuracy of about 95%. We did not find any benefit from external images obtained from naval history or uboats.net, which is quite surprising. We also clearly illustrated that the interplay between image segmentation and safe augmentation and the importance thereof to boost the performance. And we also illustrated how Grad-CAM can be used as a very nice, attractive visualization method for interpretation. There's a plethora of topics that you can think of for doing future research. Since this is a quite generic methodology for which we now have a code pipeline available, we will apply this methodology in other settings. So we're talking to other types of museums around the world and digital archives to see whether we can implement it there. We can also, instead of using Grad-CAM as an explainability tool, look at other things like counterfactuals, is something that is very much interesting to us, but also Shapley values is something that we will look at. So very exciting research. I hope you enjoyed the presentation, and I'm happy to refer you to the paper for more information. Thank you very much.